Hello everyone. That's the class for Wednesday, July 13th, and we are talking about energy equation and conservation of energy, which is the first law of thermodynamics. Today we are going to finish till end of chapter 5, and homework for that is released, and the deadline is next Thursday. So on Friday I will solve some question like recitation, but today we will just finish this uh, chapter, and we develop the conservation of energy, how we can simple that, and how we can apply assumptions. So first, let's start about the first law of thermodynamics. As you can see, that's the first law. Okay, first law of thermodynamics. Thermodynamics. In for a system in a world. Okay, so as we see, that's a recall, so that's something from the thermodynamics course that you already passed. What does it mean? It means that time rate of increase in stored energy of a system, it has to be equal to the net heat into the system and the net rate of work transferred into the system. As you remember, it has to be shown by Q dot N. Q dot N means Q dot net in, and W dot net in for a system. And from the conservation of mass, energy, and conservation of momentum, you will remember that this is the capital D, means total derivative of energy in a system, and capital E means the total energy, right? But lowercase e is also defined as a total specific energy of a system that is per unit mass. Per unit mass means that we are going to get rid of the mass of a system and get define that as an integral form for a system. And since each of those control volume, the small volume of particles has by itself has a volume, then multiplying that by rho, it means rho v gives you the mass, and mass times E going to be capital E for a system. And it has to be equal to Q dot net of in and W dot, that the work is done by system or on the system, and Q dot is the total energy that goes in or goes out. So we can define the energy here, the total energy, as three terms. That the first term is internal energy, again per unit mass, and the second term is the kinetic energy term, again per mass, and that's going to be your potential energy. Summation of all these three going to give you the total energy stored in a system. And also, if you multiply it, you show that with the lowercase e, it means that you have to be per mass, as you see here. And if you multiply that in the total mass of your system, you will have total energy, or capital E of a system. As it's showing here, again noting that E is going to be EM. M is mass of the system, and then mass also can be defined as a rho the total V or dV, then also you need to integral over the control or over the total system. If you apply the Reynolds transport theorem, the same thing that we done for the conservation of mass and conservation of momentum, then you can relate the system to control volume. That's the Lagrangian to Eulerian view, moving from system to control volume, and the total derivative of uh, uh, energy of a system is equal to the time, the partial derivative of time derivative of the amount of energy that change over the control volume inside the control volume, and all the energy termed, all the energy that passes over the control surface. That shows by E rho V dot NdA. And you remember that we had a B term that for mass was 1, and for momentum is V, and for energy is going to be lowercase e. And what is that totally is your conservation of energy. When you are going to apply conservation of energy, you have to apply this. But it by itself is again confusing. So I wrote it down a number here to make it simpler. That's equation 1, and that would be your equation 2. Okay? So you remember that we can replace or substitute 1 into 2. Why? Because the left hand side in equation 1 is the total derivative of energy of a system, right? And is equal to be by the net rate of heat transfer into the system and net rate of the work transfer into the system. So we can replace that here, and we get another equation, which is equation 3. So by replacing 1 into 2, okay? So simple, just bring it down to add these two equations and have a more general equation. Again, we don't need to analyze system. That's much easier for us to analyze the system, analyze the flow based on the control volume and control surface, because these are fixed in the space and domain. That's why we replace this one with that. Okay, and again, that would be on control volume, because that's based on the control volume in the analysis. So what does it mean, the Q dot N? The net rate of heat transfer into the control volume. Okay, so it could be defined as a net heat that exchange between your control volume and surrounding. Okay, and what about the W dot? Is net rate of the work transfer into the control volume. It could be in terms of power, also known as power. That's W dot. That's the energy that exchange between the your control volume and surrounding in terms of in form of a work. Okay, so perfect. But the only thing that is left, we need to list our assumptions here about the signs. What are the assumptions? First, if the Q comes into, that's the Q is total energy, and Q dot is the net rate. So we are talking about the energy in terms of the total energy, not the rate, but it could be also the rate. But the Q that comes into the control volume, consider as positive. The Q that goes out of your control volume is negative. Okay, about the work, the work that is W is the work, right, that done by the control volume, it means that, for example, expansion of your control volume, if it's done by the control volume, then it's going to be negative, and if the work done on the control volume is going to be positive. That's the only thing that you need to know. If the work is done by the system, it means that it's doing work on surroundings, so get energy to out of it. So this side should be negative. But if the work on the system happens to the work on the control volume, then it has to be positive. That's all. So what next? We have to define, you have to review that what type of works we have. So because energy could be in terms of heat, right? That's something that increases the temperature, or if that's adiabatic, the Q is going to be 0. But work has different shapes or different definitions. Like, for example, you have type of shaft work, okay? The shaft work means that the work due to the torque. And it happens in most of the rotating devices, such as a fan, or the engines that has shaft. And the torque, if you define that this torque is torque of the shaft, the total work, and the omega is your angular velocity. So if angular velocity, and that's your torque, then multiplying these together is going to be your work by shaft, or shaft work. You have another type of work that is because of external exerting a normal stress over distance. It means that the force, the pressure and the force that you have on the inputs, outputs that you have as a normal, or it could be in terms of the tangential stresses like tau that you have because of the close to the walls, and when two fluids have two layers of the fluid, that you have a tau between those, or tangential stress there. Okay, these are type of the works could be done on the control volume or by the control volume. In terms of W dot net in, the total is going to be sum of all these. Okay, whenever you have it, and sometimes you may not have it. So we talk about W dot shaft, that is going to be T of the shaft times omega. Now we are going to talk about the normal stresses, right? Normal stresses is also due to is type of the pressure, that pressure doing work. Okay, so for example, you have in inlet and outlet of the, for example, in the inlet, the flow comes in. You have a pressure here, right? And the normal direction is in this way. So the total work is going to be defined as a force times velocity, right? And delta means that the small amount of that. You can replace the force by pressure times area, right? So sigma n delta A is going to be your force times V, okay? So velocity is in this direction, right? Velocity comes in, pressure in this direction, and n is outside. So we define that sigma always is minus P in terms of direction. So sigma is a tensor actually, but in normal direction so sigma is actually has a direction, okay, and it is in direction of n. That's also an assumption here. So if you're going to replace sigma n, you can bring sigma as minus P and bring V dot as V dot n. You replace that in this way and rewrite it, then you can write that W dot is going to be your delta A or dA, and get the integral over control surface. So whenever you have inlet or outlet or pressure that is on the flow or control volume surfaces, then you can get the W dot the same that you did for momentum or m dot, which is the mass that comes in and going out. So the P V dot and dA, this P is going to be your B based on the Reynolds transport theorem. So also because of the N is under the different direction with P, you have a negative sign here. So minus P V dot N is going to be your equation for W dot whenever you have it. What else? We have tangential stresses, which is the tau, and it could give you the because of viscosity you will have shear stresses, which is in tangential direction, and you may sometimes have work by it. Okay, so but most of the time is going to be zero or negligible. There is a reason behind that. First of all, let's think that you have a shaft. Okay, and this shaft is turning, right? That's the turning, which is the direction of omega. So if you see, that's my A prime, and if you check the A prime view, you have a shaft that is going to turning with the omega. Okay, and because of that you have tau here. Okay, so also it should be in the other direction because that's like type of friction. But that's omega, right? The velocity comes from r cross omega, so the velocity is actually in this direction. And if you check it out, velocity is always normal to the surface, and tau has a 90-degree angle between these two. There is 90-degree angle. Or let's check the pipes. In the pipe, you have a velocity profile, right? If that's your pipe, then that would be your velocity profile in general. And here you have V equal to 0, right? If you have V equal to 0, then you know that the work is force times velocity. When the velocity is 0, then it's going to be 0 because V of the wall is 0, right? That's another type for W dot because of shear stresses, or W dot tau, that we are saying that this is mostly negligible or 0. So W dot of tau could be 0 if in one of these two relation, one of these two condition, or that the V is normal to tau direction, or V by itself is 0. Right? That's the way that we could be 0. But in terms of equation, if you have by chance you had it, then the same definition is for W dot of tau, force times velocity, and the force is going to be tau times area, right? Times n area, and you can bring the V dot here, and you can write that the same here, that is going to be V dot n, right? Tau V dot n. Okay, so if the tau and n is normal to the direction, and if the tau and V dot n is 0, like what happens in the shaft, and also if the V is by itself is 0, then you can say that is 0. In this course, you mostly talk about the pipe flow, and in pipe flow, this type of works are 0 because velocity, the tau happens in the Most happens in the wall, close to the wall, that you have uh, 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 the change of velocity there. But because velocity at the wall is zero, then for the pipe flow, this type of work is zero. Velocity at the wall is zero, then W dot of tau is zero. Let's finalize our work here. Okay, so you know that in types of uh, the in types that you have velocity, pressure at the inlet and outlet because of normal stresses. So you can replace that here. That okay, this is one of my types of work, and you get rid of the W dot tau because you see that most of the time is zero, right? And still you have W dot of shaft if you have a shaft. Q dot in by itself could be zero if adiabatic is that. If not, you have to take care of it. Okay, so W dot shaft, you replace the W dot net in with the W dot shaft, W dot sigma, which is the pressure, and you get rid of the W dot tau because most of the time is zero. Okay, and now the rest of this is the same as equation 3, that is your control volume and control surface terms of integral. Okay, and if you finalize that, you will have another equation, which is Q dot not net in plus W dot shaft net in. You have it here. You can bring this integral on the other side, and since it's control surface integral, you can sum up with the E term. And also you remember that we define E as U bar plus V squared over 2 plus GZ. That was your internal energy, kinetic energy, and potential energy. If you replace all together, then replace E and sum up all together, then you will have U bar V squared over 2 GZ, and you have rho V dot NdA here, right? In this term also you have V dot NdA, but you also have a rho here. You have to bring a rho in the denominator for P because P doesn't have it, right? So the P over rho, this is going to be your term that the energy could passes over the surface, control surface, because normally this mostly happen in the inlet and outlets. So that's why you have it. Again, I'm writing here that this is the pressure effects at opening. Okay, so great. You have an equation that is your another writing for another form of the conservation of energy. Okay, to keep that, now you can talk about more simplification that is based on the assumptions. For example, if the flow is steady, then you can get rid of the steady state, get rid of the partial derivative term because it's going to be zero. Okay. Another thing that if the properties are constant or the flow is uniform, the integral over the control surface is going to be this. Why? Because if the flow is uniform and the properties is constant, means rho is constant and it goes out of the integral term, and V dot N, because that's uniform, you don't need to get integral over the whole area because the flow velocity is uniform, right? You can multiply V by A, and that's going to be your average velocity is the same as your velocity locally, spatially changes. It doesn't change. If you have velocity profile, it means that the velocity, like the equation bonus equation in the homework, that in the input you have uniform velocity, then you can write the integral in very simple, right? You don't need to get integral. You can say that okay, V bar or average velocity is the same as the velocity, local velocity in each point, then I can say that rho AV going to be m dot, right? But when the velocity has a profile locally changes, you get the integral of that. You cannot say that is going to be v bar equal to v, because v is always changing, and you need to get the velocity average to find it out that how much of the m dot is going to pass over the surface. If the flow is uniform and rho is a constant, then you can say that these are all constant coming out, okay? Then I bring it out here, this stuff, and then the integral going to be your m dot. And what you see that m dot out and dot in. Why? Because m dot out, the velocity and the n has different direction. So v dot n gives you a negative sign because it's input, and if it's output, going to be positive sign. So it's going to be summation of all the energy that passes over the your control surface. Again, that means that if you have the control surface that passes over that, okay? But again, if you check that equation, you still have type of the W dot shaft here and Q dot N, Q dot net that passes over, added to your control volume or going out of that. It depends that how much time you have Q dot and W dot shaft. So most of the time this is not shaft or rotating devices, then W dot shaft is going to 0 and Q dot net is going to be 0. If not, the question will tell you that okay, that much of the energy going to pass as a heat to the control volume or out of control volume, then you can say that okay, the summation of these two should be equal with the left hand side that you had in the conservation of energy, like Q dot net, and if you have a shaft you can calculate the W dot N. But these are all based on assumptions, okay? You summarize that, you simplify the right hand side, but left hand side by itself is easy to calculate. The Q dot is given most of the time, or it's going to be like mc delta t, and the W dot shaft is also based on the torque and on angular velocity. Calculation of those are easy. We are talking about the control volume part, that's much harder, okay? And it's possible that like pipe flow you have only one stream entering or leaving, okay? If you have only one entering and one output, then also this is going to be your equation. What does it mean? It means that most of the time you consider a stream tube. A stream tube is actually a combination of streamlines. You can assume that you can physically understand it by see that you have wires and you have cable that are underground, right? For example, for internet. If you check out in the underground when they're doing the work, you see that you have a huge cable that inside of that you have thousands of the small diameter wires that goes for each house maybe, okay? So the whole cable is going to be your stream tube, and each wire is going to be one of your streamlines. But why we are assuming that? We are assuming that because that's going to be very small dA, and in this stream tube, then you can assume that the velocity here and here is uniform, and you have one inlet and one outlet, because the flow passes over the streamlines. And if you check the particle here, all the particles that comes in from this side going to pass over a streamline. They are not going out because that's your streamline, and it passes over here, that is your output. Since also this is one particle, you will tell me that okay, maybe particle goes there because that's pass line, this is streamline. Yes, you're right, but we assume that this is a steady state. Then if the steady state is that a streamline and pass line and a strip line all are the same. That was from chapter 3 that we talk about the Bernoulli. So when you found out that a streamline for a flow, and you found it out that it's a steady state, then you can say that streamline, pass line, and strip line all are the same. So if one particle comes in here, it doesn't go up or down, it passes over the streamline. So any particle that start to moving from this point is going to pass over the streamlines and goes out. This is another thing. Maybe you most of the time you don't use it, but these are type of assumptions that you can apply. Okay, you may have it, and you will understand that how you can summarize or simplify your conservation of energy. It doesn't mean that always you have that in your question. Okay, so in this type of thing, when you have a steam tube, again the rho v dot n term dA could be summarized and write it down as a rho AV, and this is going to be your m dot. It could be for in or out. Okay, this is also another type, but here we have another thing that we can assume that the u bar plus p over rho, the pressure over the density, is going to be your enthalpy. Okay, if you assume that, then you may have enthalpy as an input for or known in your question, then your equation could be summarized in this form, right? These are all type of conservation of energy, but for example this one is mostly for the mostly uses for compressible flow, not for incompressible. When the flow is compressible. As I talked to you before about the compressible, means that rho is not constant, and we talked about that before, that in this course, in this level, you are not talking about the compressible flow. Mostly just the question are incompressible. So most of the time you are not using that in the homework or also in the exam. And also the comment mentioned that shaft work is inherently unsteady. Yes, sure, but it is unsteady because the velocity always change by time or locally. You have the unsteadiness because of location. If you see the velocity is not constant, because the velocity has angular velocity has direction, and all the time at any time is moving, right? It doesn't change, the amount of velocity doesn't change, or angular velocity doesn't change, but because of its direction changes continuously, then absolutely is locally unsteady, right? Because the velocity change by time, then you can don't assume that is steady. But if you assume that there's a cyclic part and recurring happen, then you can say that each cycle again going to repeat it, and you can assume that based on the cycle by cycle or cyclic work is steady. This is also another type of assumptions. And finally, we are going to talk about very important things here. Okay, let's bring all assumptions all together, and that's the thing that most of the time will ask you question in this level. If the flow is one-dimensional for conservation of energy, so if you assume the flow is a steady state, that yes, we can assume that. So if the flow is a steady state, then means that partial derivative term is going to be zero, right? If the flow is one-dimensional, the one-dimensional means the uniform flow. When uniform flow, you can bring m dot out because the rho AV, you don't need to take care of the integrals, right? So the m dot going to be rho AV, and you can find it out that the v bar is equal to local v, and you don't need to take integrals here. Okay, so incompressible flow means rho constant, and constant properties means such as temperature and viscosity, like other properties like viscosity, or temperature. These are also constant. So yes, could be possible. Most of the time temperature is room temperature in this type of questions, and yes, it could be constant. And one inlet and one outlet. Okay, so if you have one inlet for the flow and one exit, then what you will find it out that if you assume if you apply the conservation of mass, and since the rho is constant and the v is uniform, then you have to know that the m dot of in is equal to m dot out, and you can say that this is going to be your m dot, right? By this assumption, the m dot in, because you have only one inlet and one outlet, what you can write, you can write that, okay, whatever rho is constant, it has to be m dot in equal to m dot out, right? Because you do only have one inlet and one outlet. Whatever v's could be different in v in could be different with v out, right? Because you most of the time have different energy, so it could be different. And also velocity changes, or maybe area, like a nozzle area, could be different. But what we know that m dot, the total mass, is conserved, right? So m dot in has to be m dot out. Why? Because we have one inlet and one outlet. Then these two could be similar and one m dot, right? We wrote it down here that we have one m dot. What else we can assume here? We can define the q dot net. Q dot is the total, the rate of the heat that comes in, okay? But the heat by itself, it could be in terms of the flow, right? So for example, you have like a pipe, okay, and you have two pipes that are connected. The flow comes in and they are mixed, but the flow from pipe 1 that connected to the flow that is pipe 2, like pipe 1, pipe 2, and then these are going to be the same, okay? So if you assume the control volume is here, this is your input and that's your input, and you have one input or one output, or you can assume that, okay, this is my input, right? And control volume is here, right? You have one input, and the flow that comes in could have a different temperature with the other one. So by itself, if the flow comes in, it brings heat to your control volume, right? So if you assume that this is going to be your types of m dot, because q dot net, it could be defined as the m dot, which is your mass flow rate, times the q net, which is the amount of energy as a heat per unit mass, okay? And if you assume that w dot net is m dot times w of the shaft, the w again is the work per unit mass times m dot. If you assume these two, then you can cancel out all the m dots from each side, right? Because these two terms also have the m dot, and you have another m dot here, okay? So you can cancel out m dot from each side. Perfect. So what we'll have left, we have q net in here, w shaft net here, and m dot goes out. You don't have any time rate change here, because these are all m dot goes out or cancel out. And what else? If you see here, u out, u in, p out, p in, and v out, v in, z out, z in. But you can sum up these two with the q net that you have the other side, okay? U out minus U in minus Q net. If you bring that to other side, you can assume that this is your loss, okay? Just assume that. We'll talk about that, why this can be assumed as a loss. So we can say that our loss is going to be your U hat out, energy that total internal energy that goes out, minus the total energy or internal energy that comes in, minus Q net. Okay, just assume that. Again, define that. Doesn't mean that it has to make sense. but the final equation would be make sense. There is a reason behind that. We'll talk about it. Okay, so you did that. What else left? If you assume that these two terms plus Q net is going to be a loss, then what will left? P out, P in. So the total term that you have here, M dot cancel out, and you have a W shaft here. Keep that the other side. We don't care about it right now. But is that P out, P in, and V squared GZ familiar to you? Isn't, if you bring the negative sign, keep that as equal to 0. If you assume that this is 0, and you don't have any loss here, so you don't have any W shaft, then it's going to be 0. And you assume that the internal energy and the Q net that you have here, or loss is 0, what will be left? That this term is going to be 0, right? If you say that this term is going to 0, and bring all the negative sign to other side, this is going to be your Bernoulli equation, right? That's a Bernoulli equation. It means that if you don't have any loss, okay, what was the assumption for Bernoulli? It has to be over the streamlines, a steady state, incompressible, and for the over the streamlines, right? What was the other assumption? Steady state, it has to be one-dimensional, input and output incompressible, constant properties, and steady state over the streamline. That's it. So all the assumptions are valid here. You can write it down that over the streamlines means that for input and output you have a streamline, and you can write it down the conservation Bernoulli's equation. Okay, so Bernoulli's equation by itself is when you don't have any loss. Okay, the other, what we don't have any loss, because in the last assumption that we forgot about it, I couldn't remember, that is viscosity. So we had another assumption in Bernoulli that the flow is inviscid, right? What does it mean the flow is inviscid? The flow is inviscid means that you don't have any loss of energy because of the friction. Okay, so when you don't have any loss of energy as a friction, you don't have any Q net because of the loss of friction. You know that friction change energy of kinetic energy to heat, right? So inviscid flow means that the Bernoulli assume that you don't have that Q net, so the U out, U in are going to be equal, then it's going to be 0. If you don't have any work on the system or over the streamline, okay, so this is going to be 0, and since you don't have any loss, the Q net is also 0 because the flow is inviscid. Okay, then what will left? That the Bernoulli equation is valid. So why we assume this? We want to show you that the conservation of energy, if you don't have any loss or any work on the control volume or by the control volume, then internal energy is the same. If internal energy is the same, then you have Bernoulli equation. Okay, so we can rewrite this equation as a mechanical energy equation, that P out over rho, V out squared over 2 for the out part, and GZ out is equal to, for the in part, the input part, plus two terms, W of the shaft minus loss, right? So what we did, we bring two assumptions that we, or definitions here. So U bar, U hat, we bring U hat minus U hat in, and Q net with sum of all as in loss, and keep that in the positive side, right? So we keep that with the input part. Okay, so that's why loss has a negative sign, because we bring that to other side. So loss, W shaft, we keep all here, and the output equal to that. But what else we can do? We can write that, we can multiply each side by 1 over G. Okay, so if you multiply by 1 over G, by multiplying that by 1 over G, then 1g going to multiply by rho, then you have gamma, rho g. 1g comes in here, and the g here going to cancel out. The same here. What we left, W shaft over g minus loss over g. And again, loss is u hat out minus u hat in minus q net in. Okay, so this is going to be over g. What's the name? Just let's give the name to each. This is going to be your total head. These terms, the Bernoulli thing, so till here, this is going to be your total head of energy. Okay, and we'll show it by capital H. Okay, so if it's for output, then total head in output, and here you will have total head or H in. Okay, what Bernoulli is mentioned, Bernoulli mentioned that if you don't have any loss, any work or anything to suck up or add energy to your flow, then total head energy should be conserved. Okay, then total head for the output and input, or means that over a stream tube. That's why we assume that is a stream tube, because a stream tube could be extended to all the flow like a pipe flow. Okay, if you assume that this is 2, we don't have any loss in these two terms, then total head going to be conserved, and total head in and out should be equal, and that's your Bernoulli equation. So we extended the Bernoulli equation, but since the Bernoulli is familiar to you, we keep that here. We add two terms there, that is our loss and work. Okay, so we put the two names here, which is HS and HL. This is going to be your shaft work head, and that would be your loss head or head loss. And you remember the W shaft, we assume that the W shaft, so for H loss, you have U out, U in, and Q net in, right? But you assume that this is your loss, and you bring the M dot out, right? But here, if you assume that the job, the work is W dot, that's the total net rate in, over M dot is going to be your W shaft, and times G going to be your HS. Again, come here. We assume the W dot shaft is M dot W shaft, right? So W dot over M dot is W shaft, and over G multiply G on the denominator. They're going to be your head shaft work head, and this is going to by itself a loss. Okay, loss over G, and this is going to be your head loss. So let's summarize all together and write it down, or final equation. So H, or total head out, it has to be equal to total head in plus the shaft work head minus the head loss. And what about Bernoulli? Bernoulli assuming that if there is no loss and there is not any work by the system or on the system, and if these two are 0, then no work and no loss or implicit, right? Then H out should be equal to H in. What does it mean? It means that the P over rho g plus V squared over 2g plus z, that is your pressure head, velocity head, and the height or the potential head. These are going to be conserved, right? It has to be equal from input to output. That's all for the chapter 5. In the next class, I will solve some question for you, and this is going to be it was because we split that this chapter because it was very important chapter to talk more about it and give you time to read and follow the materials. So this class is short, and we split that to four sessions. First, the conservation of mass and momentum, then solving or recitation or solving some question for mass and momentum, then define how we develop the conservation of energy and the equation for the energy, then relate that to Bernoulli's equation. And now the next class I will talk about the some questions that not only use the conservation of energy, but also again you need to apply all three rules: conservation of mass, momentum, and energy. Why we need that? Because conservation of mass is relate the input and output gives you one equation. If you don't know what is the velocity input or output, it gives you the one equation. And conservation of mass, momentum by itself has 2 or 3 direction. We are talking about 2D mostly here, so it's going to be 2D, gives you 2 equation by itself, and conservation of energy also 1 equation, right? Again, that would be your depends to velocity that you assume, but it's type of energy, so it doesn't have any direction right now. So finally you will have 3 to 4 equation, and it means that your question could give you 3 to 4 unknowns that you need to apply all these step by step and follow the rules, and then find it out how much is the loss, and finally how much is the loss and how much is the shaft work head, or what is the, for example, if you have pump that if you remember the Bernoulli's chapter 3, homework 3 that I gave you, there was a pump and there was a C, and the pump the flow of water from the lower Z or the sea level into a height which was capital H, right? But in that question we assume that there is not any loss into the in the pipe. That was one of the assumptions. If you check the homework again, you will see that we applied the Bernoulli equation there, but with assumption that the flow is inviscid inside of the pipe. Why? Because we assume that, okay, we are talking about after the pump. If you remember, we talk about after the pump, after applying work from the pump, and also we assume that, okay, after the pump till output of the flow in the height of H or capital H, nothing going to change because the energy is conserved and we don't have any loss. On that part you apply the conservation of Bernoulli's equation, because the conservation of energy wasn't familiar. You weren't familiar with the conservation of energy. Okay, we have the same equation in this homework that is already released. You will see that the same figure with same equation, but with this assumption that the loss are not negligible. Okay, then it will ask you that how much work should be done by pump to increase the energy and also compensate for the loss that you have inside the pump, inside the pipe. Okay, so the flow by itself are not inviscid, but as you know that Bernoulli's equation, when we talk about Bernoulli's equation, we say that there is not any flow that the inviscid is really inviscid, and you have viscosity as a parameter. It could be very low for air or very high for oil, but it's not 0. Okay, so loss is also could be part of Q in, right? If the Q net in is also part of that, it could be because of loss or it could be because of the heater. For example, you have a pipe that the flow passes, but you put a heater behind the pipe, and it makes the pipe add heat to the flow, right? It could be type of that, but we didn't have in Bernoulli. Bernoulli assumed that there is nothing there. But now you have to take care of that with the conservation of energy. That's only going to be different from Bernoulli till here. So we assume we bring some assumptions here to again step by step reach the mechanical energy and show you what is the W shaft and loss, and assume that if we assume that these are not much high or negligible, then we will have again Bernoulli's equation. That's what we did with these assumptions to connect 2 points from chapter 3 and end of chapter 5, which is the energy equation. Okay, so next time I will solve question for you, and I hope you enjoy the class and follow the materials. Have a good one, guys.